Hello, everyone. I'm so excited to be here to tell you about our research at MIT. So I'm going to talk about something we call ambient intelligence. It is the convergence of radio signals with machine learning, particularly neural networks. So if you think about radio signals, we all live in a sea of radio signals. They are actually very powerful. Not only they carry messages and Wi-Fi packets and all that stuff, but actually radio signals traverse walls and occlusions. And they bounce off our skin. And when they bounce off our bodies, they get modulated by everything we do, by our steps, by our breathing, but by the pulsing of our blood. So even more than that, in fact, they change when we go to sleep, when we enter REM, which is the stage in which we dream, and not only this, they actually change according to our diseases and our health and activities. So if you step back now and say, can we design neural networks? Can we design systems that would leverage machine learning, neural network, radio signals, and analyze these radio signals that bounce off people's body to understand how they are moving, their respiration, their vital signs, maybe even diagnose diseases before doctors can diagnose them. Now, this sounds like science fiction, but actually this is exactly what I'm going to show you that we did. And let me progress to the next slide. So this goes back to like several years ago. This is one of my students. This is our offices at MIT. And we put our wireless device not in the same office, but in the adjacent office behind the wall. So you see a big arrow says the wireless device behind this wall. And this red dot here is where the device thinks this person is now standing. Now, I'm going to play a video, and what the wireless device in the adjacent office is going to try to do is to try to kind of see this person through the wall, track his motion, and be able to localize him at any point in time without having this person wear sensors, wearables, nothing. It's just based on how his movement changes the electromagnetic waves. Let's see. So look at the red dot. And as he moves from behind the wall, we actually detect how he's moving, where he is at any point in time. And we can do it pretty accurately without any sensor on his body. In fact, for all practical reasons, he might be oblivious that we are monitoring him from the adjacent office. Quite accurate, isn't it? So, of course, everything that we measure, we compare to the gold standard. In this case, it's a whole room with infrared cameras and infrared marker on the person to show that we can localize and track him very accurately. So this is, I told you, this was several years ago. So let's fast forward and see whether we can do better now. Okay, now I'm changing the frame. The big frame is what the wireless device sees from behind the wall. And that image there is just for you to know what's happening inside the room. And now what I'm going to show you is not only we can see a dot with a person from behind the wall, we can actually get a whole stick figure of how the person is moving. When he sits, not only a dot stays in the same place, actually there is a stick figure that sits with him. So you see, he's sitting. The wireless device knows behind the wall that he's sitting. The other people are walking. When they step with the right foot, he knows that they are stepping with the right foot. When they step with the left foot, they know, the wireless device knows from behind the wall. So kind of like we got X-ray vision. Not only this, now we can actually understand people's actions and activities just using radio signals. So you're going to see that stick figure at the top, which is what the radio signal is getting. And this is just for you so that you can see what the person is doing. Now, you see when he emulates combing his hair. So let's see. That stick figure is combing its hair. It's like drinking. The wireless device knows that he's drinking. So we have a form of X-ray vision that allows us to know what people are doing from behind the wall. Now, I don't have time here to tell you exactly how it works. Of course, it's a complex system. But what I want to emphasize is really about the convergence of two things, radio signals and machine learning. Radio signals are the ears of the device. So that wireless signal that bounces off our bodies and spread in the environment and goes through walls is very minute, actually. And if the device did not have good ears, did not have good design for how to understand and integrate and capture this minute signal, we wouldn't be able to do anything. But ears alone don't matter. I mean, as we all know, I mean, we need the brain that can explain those signals. And that is where the machine learning works. So I'm going to show you other things that we can do with this kind of analysis of radio signals with machine learning. So when you go to sleep, your brain waves change and enter different stages: awake, light sleep, deep sleep, REM. REM is rapid eye movements, which is the stage in which you dream. Now, these sleep stages are very important, of course, for sleep disorders, which we know like 1 in every 3 Americans have problems sleeping. But not just that, actually, sleep is a platform for almost all diseases. If you think about depression, for example, in depression, REM tend to happen early, too early in the sleep. In things like Alzheimer's, for example, deep sleep, the slow wave in the brain during deep sleep are correlated with Alzheimer's. So if we can understand these sleep stages, not only we understand sleep, we can actually understand a lot about mood disorders and neurological diseases. Today, if you want these sleep stages, you send someone to a sleep lab, they put these electrodes on his head and body, and they ask him to sleep like this. Now, of course, it's not a happy experience. If any one of you has tried it, probably you'll remember that it's also not really your sleep. I mean, it's not the same way you sleep at home. It's not your bed and with all of that stuff. It's amazing that this is how we monitor sleep. So let me show you our device. This is actually our device. Transmit very low power wireless signal, 1,000 times lower power than Wi-Fi. Analyzes the reflection with machine learning. And what you see here is something called the hypnogram. For every 30 seconds of sleep, it tells you whether this person is now in REM, in light sleep, deep sleep, or awake, for every 30 seconds. Now, of course, anything that we do, we compare with the gold standard. In this case, is something called PSG, and we have multiple publications that show that the system is quite accurate. Here's one person who's sitting like you guys, and what you see is a wireless signal capturing his breathing, his inhales, exhales. We ask him to hold his breath. You see the signal stays at a steady level because he exhaled, he did not inhale. And no sensors on his body, no wearables, nothing. Again, everything is compared with the gold standard. In this case, is like a medical device that the person has to wear on their body. Now, this is the same breathing signal, the inhales, the exhales. And these blips on the signals are actually his heartbeats. So even the pulsing of our blood changes the electromagnetic waves around us. And those wireless signals are very sensitive, but most importantly, the algorithms and the model can extract that information from the signal. So over the last few years, we have been working with doctors and hospitals and pharmaceutical companies on understanding diseases, a variety of diseases, Parkinson, Alzheimer's, Crohn's, COVID, et cetera. And I want to show you one thing that might sound really surprising. It is actually really a new thing that we are very excited about in Parkinson's disease. So before showing you that, just let me show you how our device, we mount the device. We mount the device in the home of the user, and we are just using the wireless signal in the environment. The person just lives their lives. They don't have to do anything. Okay. Parkinson's. So Parkinson's is the fastest growing neurological disease in the world. Now about like 2% of the senior populations have Parkinson's, and this is growing at an alarming speed. Now, the problem with Parkinson is that we don't really have a drug that cure Parkinson or even halt the progression of the disease, or that we have drugs that control the symptoms. And one very important challenge in developing drugs for Parkinson's is that you really need to detect Parkinson's very early, and you need to help the patients very early. Because once the disease has damaged the neurons, there is no going back. But how do you detect Parkinson's very early? Today, Parkinson's or even Alzheimer, if you think of many diseases, we detect them years after the beginning of the disease. So in Parkinson, we rely on motor symptoms to detect the disease, like tremor and rigidity. But that happens years after the disease has started. So what we wanted to do is, can we detect Parkinson's with radio signal before diagnosis? Now, to do that, of course, what are we going to use? We can't use motor symptoms. We have to use something different. So we went back and tried to read a bit about the early work of Dr. James Parkinson. And Jim Parkinson said that breathing actually tends to change in Parkinson. So we said, OK, we monitor breathing using a radio signal. Can we just use that and see maybe we can detect Parkinson from breathing? And if we can, maybe that has some hope to detect Parkinson's early before the motor symptoms start. So can machine learning detect Parkinson's from nocturnal breathing? We check nocturnal breathing. We design specialized neural networks that operate on that signal. And the neural network has to do two things. You give it a nocturnal breathing, one night of breathing of the person, and you ask, does this person have Parkinson's? And if he has Parkinson's, how severe is the disease? And we not only use our wireless signal, we also went ahead and collaborated with Mayo Clinic, MGH, and University of Rochester to get a lot of signals, many patients, and ask these questions on them. And as I said, because our device can collect radio signals even while the person is sleeping every night, we can ask this question every night using the radio signal without even asking the person to do any medical test. What do you think? Can it detect Parkinson accurately from breathing? Yeah, I see people are nodding. Of course, me. Otherwise, there is no point talking about it, isn't there? Yes. But actually, look at the accuracy. 90% accuracy in just taking the nocturnal breathing of someone from wireless signals and ask the question, does they have Parkinson or not? And not only this, I mean, again, we tried it even with a breathing belt so that to make sure that we can, it's not really something weird here, and we get more or less the same accuracy, around 90%. So that's very interesting, but now we want to ask the question, can we detect Parkinson before diagnosis, before the doctor tells the person you have Parkinson's? Now, we don't have many people for whom we measured them before they actually got diagnosed with Parkinson. We have a small population, so this is actually very early work, but we are very excited about the potential. So here what we have, in red, healthy individuals, 5 years in the past. And in blue, people who eventually, 5 years down the road, told us that they were diagnosed with Parkinson's. But this data is from 5 years earlier. And you can see the blue, the people who eventually developed Parkinson's. The device is saying those are likely Parkinsonian patients. And the red is just all of them never developed Parkinson, and the device is saying those are healthy individuals. They will not develop Parkinson. So that is really interesting, because you are taking something that is radio signal that we all swim in and discovering new power in them, that new power in the radio signal to diagnose Parkinson, new power in the metric of breathing. Nobody asks Parkinson patients about their breathing nowadays. And it opens up so many new things in medicine. Now, of course, we can also monitor movements with our device, and that is the standard way of looking at Parkinson. And we can discover new things. Actually, before even doing that, let me show you that not only from breathing we can tell whether somebody has Parkinson or not, we can tell the severity of their Parkinson. So on the x-axis, you see something called the MDS-UPDRS, which is the gold standard for measuring the severity of Parkinson. And on the y-axis is our estimate from the wireless signal about the MDS2 PDRS. And you can see blue are the patient, red are the people who don't have Parkinson. And we can tell not only whether they have Parkinson, but the severity of their Parkinson from their breathing. Now, of course, we can also measure their movement. So we looked at their movement. This is like the green thing at the top is our device. This patient just happens to live in an assisted living community. You see like the blue is a trajectory that spans 2 hours. It goes between the bed, the chair, the kitchen area, and so on. So we look at this trajectory of motion. And now we can tell something actually very interesting, not just that the patient is moving. So I told you today's medication, they don't cure Parkinson. What they do is they control the tremor. They control the symptoms. And look at this graph. So on the x-axis is the hour in the day. On the y-axis is the gait, the speed at which this person is moving. Now, this is something called a box plot. But I want you just to look at the red line, which is the median speed for this patient as a function of the hour in the day. And you can see that this person, okay, I mean, we all are slow during the night, but you can see during the daytime, he just has these like peaks and valley, and like his gait gets faster, and then he goes slower, and then faster and slower. Can you guys guess why? It's the impact of medication. You see it on the patient. I mean, this is like nobody can get, typically like for these graphs, you need to like do them on animals because you can never get them on people. So here's his first dose of medication. And you see the gait goes up because the drug controls the symptoms. So now he can move much faster. Then at some point, the effect of medication starts wearing off. So you see the gait going down. You see the valley. He takes a second dose of medication. The gait goes up again. Then it levels off. Then again, for every dose of medication, you see the improvement. And then you see the medication wearing off and the patient going back to the old state. And that is very powerful because now doctors can do medication titration and they can actually adjust the dose for this specific patient instead of saying, oh, for your kind of disease, your age, your duration of disease, this is what we think is the right dose for you. I want to talk quickly about COVID because, I mean, this is a disease that touched the life of every one of us. So we were asked by the assisted living community during the time, you remember, like at some point there were so many deaths and problems with elderly being affected by COVID in assisted living facility and retirement homes. So some of the assisted living facility here around us in the Boston area came to us and said, can you help us? Our residents are in quarantine, and those are old people in their 80s plus, and we can't see them. We don't know, are they doing well? Are they recovering from COVID in a smooth way, or are they having problems? So we started monitoring them. Of course, COVID is a breathing disease, or it affects the lungs. So we see very clearly the impact of that on the patient as they recover. So here what you see is the respiration of a patient on April 7, and her breathing rate was 23 breaths per minute. And just 4 days later, on April 11, the breathing rate went down to 18 breaths per minute, which is the normal, the baseline for this person. So this person is recovering. Her breathing is going back to normal. Also, what you see here is the gait and the movement. So this person on April 8, you can see like she's very slow. On April 11, she's much faster. Let's see again. So in both cases, she's moving from the chair to the bathroom. So agility and the ability to move, of course, improve when people are recovering. Now, of course, not all recoveries are very smooth. So this is the breathing of a COVID patient. But now, instead of these nice inhales, exhales, you see this like very irregular breathing signal. Really bad. Like basically, they are like having irregular breathing. Sometimes each breath has a different width and different lengths. That's not very healthy. And indeed, in fact, what we saw in our population is that this breathing data allows us actually to be able to anticipate problems in recovery. So let me explain this graph. Each one of these blue curves is a histogram of the breathing rate of the patient on a specific day. So you see the first day is April 8th, and the breathing rate is between 15 and 20, you see at the top. Now, if you look at these histograms, you see that the breathing rate was moving lower, moving away from 20 towards 15. But on April 14th, suddenly his breathing jumped up, and indeed the patient ended up in the hospital for breathing depression. So for breathing problems. Now, he stayed in the hospital for about a week, and you see after he came back, the breathing rate again started decreasing. Eventually, the patient recovered. So now what you can do is you can look at all of these patients' population. So we see 3 stories for the patient. Patients like the one that I just showed you, which during recovery, there are some hiccups that end up sometimes in the hospital. Sometimes it's possible to deal with them locally. And there are other patients whose recovery is smooth, like this one. So it was bad. He was symptomatic, but over time, he got better. And then there are those asymptomatic patients that we all know about. They have the disease. They have no problem. So this leads me to the end of my presentation. This ambient intelligence, or this ambient signal, is around all of us. What we can do with it is to extract the intelligence from it. Now, of course, as we do that, we have to be very careful because this is very powerful. It can extract people's vital signs and physiological signals and movement behind doors and behind walls. So it's very important to take care of privacy, about security of the individuals. So anything that we do, we get approval from our IRB. And also, of course, we get the informed consent of the individual with whom we are doing these testing. Thank you very much. OK, so let me see. There are so many questions. What is the sensing mechanism, and how do you isolate the relevant signal prior to feeding it to interpreting the algorithm? So we are sensing with wireless signals, with radio signals. The radio signals falls under what is known as ultra-wideband. So it's very, very low power that doesn't interfere with anything, but it's wider band. We have designed the waveform of the signal so that it makes it very sensitive to information in the environment. So this is the sensing mechanism. How do we isolate it? We can isolate it because we can isolate the exact voxel in space where the radio signal is coming from. So I can say the radio signal is coming from this individual here versus this individual versus that individual in the back based on just the voxel in space they are in. So next. How many radio signal sources, access point, did you have in the system? Also, what band and bandwidth of the signal? So in the experiment that I showed you, we use only one device. Now, of course, if somebody has like a large space, you can, similarly to Wi-Fi, you can deploy either repeaters or additional devices to cover a larger space. What is the bandwidth and the band? The central frequencies are more or less around the same as Wi-Fi. So around 5.8 gigahertz. But the bandwidth, as I said, is much wider, and the power is about 1,000 times or more lower. Do you see the industrial application for your technology? Yeah, I mean, of course, there are many other applications. Here, I focus on humans. You can think about tracking things and animals in walls, about like tracking vibration of like bridges and material. So there are many industrial applications beyond what I described here. Can this also be used as emotional AI? So of course, I mean, basically, we are getting, so I didn't present to you one piece of work that we did where we actually detect people's emotions. So we detect whether somebody is sad, whether somebody is happy, whether somebody is angry. So we show that we can do that. And the reason for why we can do it actually is simple, because we tap into the vital signs of the people. So there is plenty of work that show that if you get somebody breathing and heartbeats, you kind of like tell their emotions. Because I mean, if we are angry, our heartbeats like start going higher. But it's not just the rate, it's actually the variance and a variety of information in that signal. So the answer is yes. Would you be able to detect seizure? We are currently working with medical doctors in epilepsy, and yes, I believe we can. So, but we haven't really honed in on the exact accuracy. My Garmin smartwatch claims to track my sleep using accelerometers and possibly heart rate with radio signal-based motion sensing, be more or less same as wristband. So as the question mentioned, these wristbands, they rely on acceleration. So acceleration means that it's interpreting sleep based on the amount of motion. And it's the amount of motion on your wrist. So in many cases, like if you're, for example, not moving at all, like watching a video, for example, it can get confused that you are sleeping. So this is a method that is called actigraphy, and it's really based only on motion. But as I showed you, we can actually detect very accurately things that are different sleep stages, like REM, when we dream. Now, it is still related to motion, but because the wireless signal covers the whole body, it gets affected by the twitching, like in REM. REM is rapid eye movements. Your eyes start moving, like even if you are closing your eyes, the actual, your eye is moving back and forth during REM. And that twitching of the muscle, even though that it is very small, it affects the radio signal. That doesn't affect your actigraphy. Is there any downside of being exposed to radio signals? Not really. I mean, in the sense that, as I said, we are using signals that are 1,000 times less power than Wi-Fi. So if you are comfortable with Wi-Fi, you should be comfortable with this kind of signals because the risk and the power is much lower than Wi-Fi. Now, of course, let me just add, of course, if you stand in front of the tower, the cellular tower, that is a completely different risk. That is like a device that is blasting at much, much higher power. I don't recommend you do that. But as long as you are comfortable with Wi-Fi, this is way less, there are no danger with this. Can you isolate a specific individual in a room full of people? So there is a limitation on the spatial widths, like the spatial resolution, because it depends on the wavelengths. So if individuals are very, very close to each other, like really close, then it's hard to tell whether it's somebody like a bigger individual or it's two people. But as long as there is enough separation, I showed you, like, for example, when the guys were walking together, we were able to get all of them. How does this scale for macro detection, such as using atmosphere module as sensor for? That's very interesting. So ideas that are similar have been used by my student to actually use for satellite imaging using radio signal. So you know, if you are taking images from satellites, if they are just standard images, then they can be blocked by the clouds. While if you are using different radio signals, you can go through the cloud and you can recreate images despite the fact that the visual space can be blocked. Are all those examples interpreted real time or is all post-processed? So some of the examples that I showed you are in real time. Some are post-processed. Like, for example, the sleep is we get it at the end of the night. Because anyway, sleep has sleep cycles, so you want to know all the sleep cycle and the dependencies. For things like breathing, you can get it in real time. OK, so that is the last question. Thank you very much.